working on the test, I'm sure. Sorry. All right. Well, before we get started, I just want to check in with you guys. Wanted to see what you understand about the concept of hyperconjugation, because we've talked about it before a little bit, and some of you may have learned it in undergrad OChem classes or in research groups, but you guys remember what that is? Nah? Okay. Well, you remember that conjugation is what? Alternating double bonds, resonance delocalization, those three double bonds are conjugated. That lone pair is conjugated with that double bond, and so on. It means resonance structures. In terms of the MO picture, conjugation means and this is how Paul Savage put it 20 years ago when I was in this class, a contiguous array of p orbitals all lined up with each other. So on each of these atoms you have a p orbital that lines up with the other, and you can create a pi system of molecular orbitals. Does that sound sort of familiar? Okay. Hyperconjugation is different because it's not about it's not generally about atomic orbitals lining up together to make an extended molecular orbital. Hyperconjugation is overlap between a filled orbital and an empty orbital on adjacent atoms. And hyperconjugation is a valence bond theory concept. If you're going to do molecular orbital theory, you don't need hyperconjugation, but we use hyperconjugation along with resonance as a way to take valence bond theory and give us the same sorts of conclusions that we can make from MO theory. First, originally hyperconjugation was the idea that in a system like this you could have a no bond resonance structure that looked like this. You don't move any of the bonds or any of the atoms, you don't move any of the bonds, you just move electrons around. And what hyperconjugation sort of tells you, even though this should, I mean, as far as resonance structures go, if you're TAing a class, sophomore organic class, for undergrads, and they draw something like this, you're likely to tell them that is a minor contributor. Don't bother drawing that resonance structure, right? And that's right. It's not a very strong contributor, but it does help explain why a proton that is beta to a leaving group is more acidic than a proton that isn't. This resonance structure would tell you that that proton that's beta to electronegative atom should be somewhat more acidic than expected. Though in a perhaps more detailed way, rather than think of hyperconjugation as involving resonance structures, you can think of it as what would happen if you had a sigma bonding orbital overlap with an empty anti-bonding orbital sigma star, okay? So recall that when we use our hybrid use of valence bond theory and molecular orbital theory, we're going to still focus on bonds being electrons shared between two atoms, but we're going to remember that anti-bonding orbitals exist. And for a sigma star anti-bonding orbital, you've got a node in between the two nuclei. You've got a small lobe here, a larger lobe here, a small lobe here, and a larger lobe there. Does that look familiar? Have we talked about sigma star anti-bonding orbitals before? Sort of. Okay. I'm going to use color for the phase relationships, but okay. And you'll notice that at least on the carbon, this sigma star antibonding orbital between the carbon and the fluorine, we're going to say, remember, it is an antibonding orbital, is pointed directly 180 degrees back from the carbon-fluorine bond. And if you line the carbon-hydrogen bond up with that sigma star, you create a situation in which a filled, this is what we would draw for a filled carbon-hydrogen sigma bonding orbital. And we can, if you want, draw electrons in there. And hyperconjugation is delocalization of the sigma, the electrons in the carbon-hydrogen sigma orbital into the carbon-fluorine sigma star. We will sometimes call this sigma to sigma star hyperconjugation. Effectively, you have a bonding orbital that acts as a donor and an antibonding orbital that acts as an acceptor. It's sort of almost kind of like Lewis acid, Lewis base stuff going on in the same molecule. All right. Another view of this that I don't know whether this is useful to you or not, but if we look down the carbon-carbon bond, here's our carbon-hydrogen bond in the front. Here's our carbon-fluorine bond in the back. I'm not drawing some of the other bonds so that we don't get distracted. I'll draw the carbon-hydrogen sigma bonding orbital here in the front. And then I will draw the carbon-fluorine sigma star in the back. Recall that there's a node there, a lobe here, 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 and then a larger lobe there, which can line up with and overlap side to side with the carbon-hydrogen sigma bonding orbital. So in back is the carbon-fluorine sigma star, and in front is the carbon-hydrogen sigma bonding orbital. All right? Now, when I talk about this in my introductory OChem class, one thing that students have a hard time with is they're like, shouldn't putting electrons, sharing them with an antibonding orbital, break the bond? And that's a really good question. And the answer is that it's only partial delocalization of electrons. If you were to remove this proton and delocalize these electrons completely into the sigma star, then indeed the carbon-fluorine bond would break. And what you've just described is an E2 reaction, right? If some base removes this proton, these electrons kick there, and then the leaving group leaves. So that does happen, and it's why the E2 reaction can happen. But in the absence of some base to remove the proton, no, it's just partial delocalization. Another way of thinking of it is you can think of it in terms of molecular orbital theory, mixing of a carbon-hydrogen sigma bonding orbital with a carbon-fluorine sigma star. So a bonding orbital would be if we've got energy here, the bonding orbital, the sigma CH bonding orbital has electrons in it, and it will be at some level, and then much higher up in energy will be the carbon-fluorine sigma star, which is empty. And this is perfectly fine. We've done things before where we've made bonds by bringing together two orbitals, and then and each has one electron, and then we make a bonding orbital. But the issue with where how many electrons each partner has isn't important. When we mix two orbitals together, as we have seen, we make one that's lower in energy, and we make another that's higher in energy. And when your two starting orbitals are far apart, recall that the amount of stabilization is small. And so your lower energy combination is still going to look mostly like a carbon-hydrogen sigma bonding orbital, but a little more spread out, and the electrons get to go lower in energy because of that. Similarly, your minus combination is still going to look mostly like the carbon fluorine sigma star, only it's going to be spread out a little bit. This is what we're going to use. So the consequences of hyperconjugation are the electrons in the carbon-hydrogen bond spread out a little bit, and also the sigma star spreads out a little bit onto the neighboring proton. This is why if we draw this molecule, if we draw this molecule in Spartan, let's see if it has it. Yay, it's in the database. And we look at HOMO and LUMO. What the heck is that? Sometimes the LUMOs look weird. Yeah, we're not going to worry about that one. Let's use a better leaving group. So there's the bromine. All right, that's better. So the LUMO here looks like the sigma star antibonding orbital between carbon and bromine, but some of it is on that neighboring hydrogen, right? And that's what we would get if you imagine adding together, this would be the plus combination of sigma CH plus sigma star CF, and this would be up here the minus combination sigma CH minus sigma star CF. Okay, so one of the consequences of hyperconjugation is that what you think of as the LUMO of this molecule spreads out a little bit onto that adjacent beta proton, and therefore when a nucleophile approaches this molecule, it's going to have to decide whether it's going to attack at the carbon or at the beta proton, and this is why SN2 and E2 compete with each other. All right, questions about that concept? All right, so in any donor-acceptor interaction, even with Lewis bases and Lewis acids, we like to know what are the good nucleophiles, what are the good electrophiles, what are the bad nucleophiles, what are the bad electrophiles. Similarly, in the hyperconjugation picture, we can rank which kinds of sigma bonds or which kinds of filled orbitals are particularly good at donating electrons, and we can also rank which kinds of empty orbitals are particularly good in donating or accepting electrons. So for our donor orbital, better hyperconjugation would occur with higher energy electrons. So you would predict that the best donors would be lone pair electrons, which we sometimes call N. Okay, these are going to be better than bonding orbitals. And if you have a choice with lone pair electrons, we're going to rank their ability to donate opposite of electronegativity. So for example, if you had a lone pair on carbon, that would be a better donor than a lone pair on nitrogen, which would be a better donor than a lone pair on chloro, which would be, oh, hold on, that would be a better donor than a lone pair on oxygen. And of course, we've talked about how sometimes you can think of two different types of lone pairs on oxygen. There's a P-rich lone pair, which would be higher in energy than, say, an S-rich lone pair on oxygen, which would be better than a lone pair on fluorine. And that's the idea is that electronegativity literally means that electrons on that atom are held lower in energy. The lower in energy we go, the worse our orbital is going to overlap with the empty high energy orbital. So higher energy electrons are going to be better donors. In terms of bonding orbitals, we're going to see that bonding orbitals between carbon and hydrogen are going to be better donors than bonding orbitals between nitrogen and hydrogen, which are going to be better donors than bonding orbitals between oxygen and hydrogen. Again, this has to do with electronegativity. Nitrogen being more electronegative than carbon, a sigma NH is going to be lower down in energy than a sigma CH. And because oxygen's even more electronegative than hydrogen, or than nitrogen, a sigma OH is going to be even lower in energy. You see the idea that as you start to involve electronegative elements, your orbitals start to move lower. And that's going to make you a poorer donor. All right, and in terms of acceptors, and there's more there that your text talks about, but I think that's maybe enough to get started with. In terms of empty orbitals that can do accepting, the best would be, say, an empty p orbital that's just non-bonding, because that's very low in energy relative to anti-bonding orbitals. And we're going to follow electronegativity trends here as well. If we think about energy, here might be, say, a carbon-carbon sigma star anti-bonding orbital. If you involve electronegative elements like nitrogen, that's going to pull the orbital downward. If you get more electronegative, say an oxygen-carbon sigma star, that's going to be even lower in energy. And then, say, a carbon-fluorine sigma star would be even lower in energy. So electronegativity takes both bonding and anti-bonding orbitals and just shoves them downward, moves them downward. And so you're going to have, for example, if you have a choice in a molecule, a carbon-fluorine bond will be a better donor, or a better acceptor than a carbon-carbon bond. There are other trends, though, in terms of acceptors. You've got the electronegativity trend, but you also have a bond strength trend. And therefore, we will see that carbon iodide sigma stars are better acceptors than carbon bromide sigma stars, which are better acceptors than carbon chloride sigma stars, which are better acceptors than carbon fluoride sigma stars. And this really does track with bond strength. If you go look at a bond strength table, carbon iodide bonds are weaker than carbon fluorine bonds. One of the reasons they're weaker is because iodide is much bigger than carbon, so the carbon iodide bond is longer, and longer bonds are weaker. Similarly, you would expect a carbon-sulfur bond to be a carbon-sulfur sigma star to be a better acceptor than a carbon-oxygen sigma star because, again, this size difference, the carbon-sulfur bond is longer and therefore weaker. Okay.
Dr. Price,
yes?
I thought iodine is like a good leaving group.
It's a very good leaving group, yeah. And what that means, and the reason it's a good leaving group there's, multiple reasons that you can think of it being a good leaving group. One of them is that once it's gone, iodide is very stable on its own because it's large and polarizable, and it spreads out electrons over a large area of space. The other idea is if we do hyperconjugation between, say, a CH bond and iodide, just draw the filled sigma orbital and the empty sigma star, that kind of interaction will be better because remember I told you that the carbon iodide bond is weak, and that means that the carbon iodide, if up here is a carbon fluorine sigma star, we would put the carbon iodide sigma star right here, and if this is a carbon hydrogen bond, because the carbon hydrogen and carbon iodide sigma stars are, I'm sorry, I'm going too fast, getting confused. Let me try that again with a little bit more space. Remember up above, we had a carbon hydrogen sigma bonding orbital with electrons in it, and we mixed it with an adjacent carbon fluorine sigma star. And because they were so far apart in energy, we got only a little bit of stabilization, right? And this is the carbon hydrogen plus the carbon fluorine sigma star. In contrast, because the carbon iodide bond is much weaker than the carbon fluoride bond, that means the carbon iodide sigma star is lower in energy than the carbon fluoride sigma star. And that means that this antibonding orbital, the carbon iodide sigma star, overlaps better, mixes better with the carbon hydrogen sigma bonding orbital, such that you get a more stabilizing effect for hyperconjugation between the carbon hydrogen orbital and the carbon iodide sigma star. Did that help? Okay. Sorry, I get confused. Okay, with that in mind, we have some tools to explain a lot of what are called stereo electronic effects. So last time, I think we started talking about when you have carbon heteroatom bonds such as CF bonds on adjacent atoms. We talked about this anti-conformation versus the gauche conformation, in which the two fluoro groups would be gauche to each other. And we talked, whoa, not even the same molecule. There we go. We talked about how you might predict that, at least in terms of sterics, having the larger groups farther apart is better. Fluorine's actually not that much bigger than hydrogen. Nevertheless, it would be reasonable to predict that the anti-conformation was more stable. But in fact, it's the gauche conformation that is more stable and is preferred versus the anti-conformation, which is less stable. So that should be kind of a, why is that? Yeah, like breaking rules, right? Well, you would have predicted that the anti would be more stable because of sterics, and if sterics fail you, then you want to go to stereo electronic effects. And the answer to this question is basically going to be to consider the two hyperconjugation situations in the gauche versus anti-conformation. So let's see. This is fine. So I think of the best way to do this. All right.' draw the sigma star orbital for this carbon fluorine bond in the front. And we're just going to draw this similarly as we have done previously. I just need a little bit more space. Oops. And then we'd have a large lobe here. Okay, and we can fill in the phase relationships or the wave function sign. Fine. All right, that is the carbon fluorine sigma star in the front. And which sigma bond does it overlap with in the back? Right, carbon fluorine. Do you see this is the carbon fluorine bond in the front, and then here is the carbon fluorine bond in the back. And that overlaps perfectly with the carbon fluorine sigma star in the front. And that overlap is kind of challenging to see. I can draw a side view if that would be helpful. Carbon fluorine sigma bond in the back. In other words, if we were to draw it this way, here is our eye looking down the carbon-carbon bond. Here is the carbon fluorine sigma star for our fluorine in the front. And here is the carbon fluorine sigma bonding orbital in the back. And you've got a filled orbital overlapping with an empty orbital. Now let's compare that to the situation over here in the gauche conformation. But before we do that, everybody good with that? See what's going on there? A filled orbital overlapping with an empty orbital. All right, so we can do the same thing over here. Again, the carbon fluorine sigma antibonding sigma star antibonding orbital in the front. Oh, I put the pink and the yellow in different places. It's okay, it doesn't matter. But now, what's different? In the gauche conformation, what overlaps with that sigma star? Or rather, what kind of bond is it that overlaps with that sigma star in this gauche conformation? So just imagine it's a carbon-hydrogen bond, right? Here's the carbon-hydrogen sigma bonding orbital in the back. Here is that large lobe of the carbon-hydrogen, the carbon-fluorine sigma star in the front. So yeah, what's in the back here is a sigma CH bond. Now, which of these two situations, sigma CH to sigma CF star versus sigma CF star to sigma CF bonding orbital to a sigma CF star, which of those situations better? The acceptor is the same, right? Which of these two is a better donor?
Sigma CH.
Okay, sigma CH, and that is why?
Because CF bonds are very low energy and ridiculously stable.
Because fluorine's more electronegative, right? Yeah, good. So it's actually better. Notice in the gauche conformation, what happens is both fluorines, the one in the front and the one in the back, both of their sigma stars get to overlap with better donors, the carbon-hydrogen bonds instead of the carbon-fluorine bonds. Okay? So it's kind of a cool effect that overwhelms whatever steric preferences are there. And this is called the gauche effect. But it's based in hyperconjugation. So this is kind of one of the times where you want to focus on the basic principles rather than the consequences, because you can memorize what the gauche effect is, but you don't need to as long as you've mastered hyperconjugation, because then you can predict that hyperconjugation would be better for the gauche conformation than the anti-conformation. All right, other questions there? So a brief application of this comes from Ron Rains's group. Professor Rains used to be at the University of Wisconsin when I was there. He's a brilliant, brilliant scientist. He's now at MIT. What I'm going to show you is pretty old work, but his research group continued to work on stuff like this for a long, long time, and it was really kind of fun. He compared 3 different derivatives of proline. Proline is an amino acid that has a 5-membered ring as a side chain. So here is just a regular proline. You've got the methyl ester, and then instead of having just an NH bond, you've got the acetyl nitrogen. Carbons in proline, this is the carbonyl carbon, this is the alpha, beta, gamma, and delta carbons. But they're sometimes also numbered 1, 2, 3, 4, and 5. And then we'll compare that. In this paper, Rains compared conformations of, whoops. And the nice thing about proline is that you can do a lot of conformational analysis by NMR, because the NMR spectrum is pretty easy to interpret. So this is 4-hydroxyproline, and then we'll do the same molecule, but we'll put, instead of hydroxy, we'll put fluoro there. Okay? And just FYI, 4-hydroxyproline is actually a very common amino acid. It's more common than, I think, tryptophan. It's not one of the 20 canonical amino acids. It's made via a post-translational modification, but it's highly prevalent in collagen, which is used as structural proteins all over your body. And they eventually started to work with some collagen derivatives based on what they learned here. We talked a little bit about ring puckering conformations, and let's see. Sorry, I want to get this right. Okay, so the ring for regular just proline here prefers what's called a C-gamma endo pucker. What does that mean? Well, if we look at this ring from the side, we'll put the nitrogen here. Here is the alpha carbon. Here is the delta carbon, and then the endo pucker for, let's see, alpha nitrogen, this is the delta carbon. The gamma carbon is going to be up, and this is the sort of endo shape, and then the beta carbon, oops, will be here, and then there's a bond to the alpha carbon there. You've got your amide group here, alpha proton, and then you've got the acetyl group. All right, so the C-gamma endo pucker is preferred for regular proline, and this is delta. And you can sort of arrange the carbon-hydrogen bonds so things are in a staggered conformation. In contrast, for the hydroxyproline, it's the C-gamma exo pucker that is preferred. Now, I don't care that you know which one of these is endo versus exo. We're just focusing on the fact that a different ring conformation is preferred. And why they call it endo versus exo, that's not important for our conversation. So again, here is the nitrogen. Here is the bond to the delta carbon. In the exo conformation, the gamma carbon is going to be down. Here's then the beta carbon, and the alpha carbon is here. There's another story here I'm not telling you about, the acetyl group, but let's just continue onward with the story. If on the gamma carbon the OH group is down, so here this OH group would be pointing in a downward sort of pseudo-axial position. Okay. Now, let's ask why it is this way. All right. And actually, since we've drawn what the C gamma endo pucker looks like, let's imagine if 4-hydroxyproline was in the C gamma endo pucker. In that case, this carbon hydrogen bond would be a carbon oxygen bond, and it would be pseudo-equatorial. All right. Based on what you know about hyperconjugation, let's see if we can explain why this is. And to do this, we're going to need to look down this carbon-carbon bond between delta and gamma carbons. So we're going to draw a Newman projection. So here is the carbon in the front, the delta carbon, and it looks like from our perspective you have a carbon-nitrogen bond here, you have a carbon-hydrogen bond here, and a carbon-hydrogen bond there, and this is your delta carbon. Everybody see where we're getting everything? Okay. Then let's look in the back. We would have a hydrogen pointing upward, the beta carbon of our ring angled downward to the right, and the OH group angled downward to the left. And in back is our gamma carbon. Now we're going to do the same thing, but again, we're going to need to look down the bond between gamma and delta carbons. So if we're going to do that, we've got to be creative and put our eyes in the page and try to look down that bond. And if we did that, again, we would see a carbon-hydrogen bond going straight up, another coming out to our left, and then the carbon-nitrogen bond would be sort of out to our right. Then for the gamma carbon in the back, that OH group, the OH group should be anti to the carbon-hydrogen bond. You see that? And then we would have the beta carbon from the ring over here, and then a carbon-hydrogen bond here. All right. Why should 4-hydroxyproline prefer this conformation instead of the endo pucker? What's better about this situation versus this one?
Is it like the same thing with the overlapping orbitals?
Yep, same thing as the overlapping orbitals. This is the gauche effect. We're not going to draw the orbitals here, but look here. The OH and the NR are anti to each other. These are both the electronegative atoms. That means that the carbon-oxygen sigma star is going to be lined up with a fairly low energy carbon-nitrogen sigma bonding orbital, which is not as good of a donor as is a carbon-hydrogen bonding orbital. In contrast, over here, look, the carbon-oxygen sigma star, which would be in back here, is lined up with a better donor, the CH, in the front. Yep. But yeah, go ahead.
Is there no hydrogen bonding in the 6-membered ring there between the OH and the carboxyl oxygen as well?
Is there no hydrogen bonding possible? 1, 2, 3, 4, 5, 6, 7. If I'm counting right, that'd be a 7-membered ring. I think that's possible. So I think to control for that, well, I'm not sure that was their intent, and I think they probably verified whether or not it has to be that way. They've used methoxy groups as an example,
Okay.
and the effect still works. But if you go with fluorine, which is an even more electronegative and therefore even poorer sigma bonding orbital donor, the effect is even bigger for 4-fluoroproline. Yeah. Okay. So there's more we could say there, but your text mentions some things that I think you ought to look at. I don't think we need to explain them in class, but your text points out that, say, in peroxide or oxygen-oxygen bonds, the preferred conformation is actually one in which the hydrogens are more or less perpendicular to each other. And that's actually also true for disulfide bonds in proteins. These are, again, bonds between two sulfurs, and again, the preferred conformation tends to be one where the bonds are perpendicular to each other. That has to do with the lone pairs on oxygen. This effect doesn't make sense if you think of lone pairs on oxygen as being in rabbit ear sp2 orbitals, but if you remember that one is S-rich and the other is P-rich, you can get that answer pretty directly. So take a look at that from your text. I think we talked about it maybe in the lecture online, but we don't need to spend much time on that now. Another stereoelectronic effect that involves a donor-acceptor interaction that you will see if you spend any time in the Savage lab, and you will see if you do anything with carbohydrates, is the so-called anomeric effect. So we use the term anomer to describe two diastereomers, the relationship, the stereochemical relationship between two diastereomers of a carbohydrate at the acetal carbon. So AC here is an abbreviation for, oops, that was a terrible place to put there we go, is an abbreviation for an acetyl group. So what I'm drawing for you now is per acetyl glucose. And this exists in equilibrium. This is the beta anomer. Here is the anomeric carbon. That's the carbon that's bonded to two oxygens. That's the acetal carbon. And through a process called mutarotation, you can trade positions. It's just via equilibrium, and we won't talk about how that happens. You probably already know acetal chemistry. But basically, we can exchange from the alpha anomer to the beta anomer. Now, if sterics were the major factor, you would predict that the alpha anomer would be less stable than the beta anomer because you've got here a larger group axial instead of equatorial. However, the equilibrium constant is like 5-to-1 in favor of the alpha anomer. So that's different from what you would expect from sterics. If it's not sterics, it's probably stereoelectronics. So what do you see different in terms of the possibility for hyperconjugation and donor-acceptor interactions with these two groups? with these two conformations, or these two actually diastereomers.
Would there be a gauche effect with the alpha anomer, whereas in the beta anomer, the two O-acetals are opposite each other, or anti?
Oh, interesting. Yeah, so they're that's fascinating. I don't think I've thought about that yet. Let's just see if we look down that bond. It looks to me like, no, I think in both of them, the acetyl group is going to be gauche. They're going to be gauche to each other. We can make a model and look at that a little bit more. Remember, the best donor is going to be a non-bonding lone pair, and we happen to have one on this carbon. And on oxygens, remember, you can think of one of the lone pairs as being particularly p-rich, almost as though it were in a p orbital, and then the other one sort of jutting out into solution in an sp2 type orbital. So if you think about it that way, and imagine a p orbital with a lone pair on that oxygen, can you see now why it might be better to have the acetyl group axial versus equatorial? If the acetyl group is equatorial, where should the sigma star go? Mostly back here, right? Whereas if it is axial, goes right back there where it can line up with that lone pair. We can call that N to sigma star hyperconjugation. I will just draw those two. I'll draw the sigma star in so you can see it. But in the when the acetyl group, oops, that's not right. When the acetyl group is axial, you have perfect overlap of the sigma star from the acetyl group with the lone pair on the oxygen in the back. Whereas if the acetyl group is equatorial, you've not really got much overlap at all. In fact, they're almost perpendicular to each other. So there's much better sigma to sigma star, N for lone pair hyperconjugation for the alpha anomer. And this effect gets bigger depending on the group you have at that anomeric carbon. For example, if you use something that should be a better acceptor in terms of the sigma star than oxygen, say chlorine, because the carbon-chlorine bond is longer and weaker than the carbon-oxygen bond, so carbon-chlorine should be a better donor. Having chloroaxial versus equatorial, that's a 1 to 32 effect. And the reason is the carbon-chlorine sigma star is lower in energy and more accessible than the carbon-oxygen sigma star. In case you're worried, this is not a chair flipping event at all, right? Because if it were chair flipping, we would need this group to be at an axial position. What actually goes on here is lone pairs on the oxygen kick off the chloro group. You get an oxonium ion intermediate that looks like this, and then chloro can come back in from below to give you that product. So yeah, the anomeric effect and the gauche effect are all based on hyperconjugation, that is donor-acceptor interactions in the same molecule. all right, I think that's probably enough of chapter 2. There's stuff we didn't talk about, but that's okay. So yeah, I will see you on Wednesday. Your exams are due at some point